Welcome to Campsphere Hub. Today, I will be presenting an important analytical technique known as atomic absorption spectroscopy, also known as AAS. This technique is widely used in analytical, environmental, pharmaceutical, and industrial chemistry for the quantitative determination of metals. In this lecture, we will discuss its principle, instrumentation, working, types, interferences, and applications in detail. Okay. Now, atomic absorption spectroscopy is a powerful analytical technique used to determine metal concentrations at trace and ultra-trace levels. We can determine the concentration at very minute level. The method is based on the absorption of electromagnetic radiation by free atoms in the gaseous state. Atomic absorption spectroscopy is highly sensitive and selective, making it one of the most widely used techniques for metal analysis. The theoretical basis of atomic absorption was known earlier, but Alan Walsh in 1955 successfully developed atomic absorption spectroscopy as an analytical technique. Since then, AAS has become a routine laboratory method for metal analysis. It is a very useful technique for the metal analysis. And it is very widely used for the metal analysis in environmental, biological, and industrial samples. Now, what is AAS? So, atomic absorption spectroscopy is defined as an analytical method that measures the absorption of characteristic radiation by ground state atoms. The amount of radiation absorbed is directly proportional to the concentration of the element present in the sample. So, absorbance is directly proportional to the concentration of samples. The principle of AAS is very simple. When a sample containing metal ions is converted into free atoms, these atoms absorb light of a specific wavelength. Each element absorbs radiation at its own characteristic wavelength. So, by measuring this absorption, we can determine the concentration of that element. So, as it is known as atomic absorption spectroscopy, so atoms will absorb the light at specific wavelength. As each element has unique absorption lines and it gives the unique spectra, and its basic principle also based on the Beer-Lambert law, as the absorption is directly proportional to concentration. Now, what is Beer-Lambert law? The quantitative measurement in atomic absorption spectroscopy follows the Beer-Lambert law, which states that absorbance is directly proportional to concentration and path length Mathematically, it is expressed as A is equal to epsilon. This relationship allows us to calculate unknown concentration using the calibration curve. We discuss the Beer-Lambert law, which states the absorbance is directly proportional to the concentration and path length. Mathematically, it is expressed as A is equal to epsilon into L into C, where L is the path length and C is the concentration. Now we will discuss the atomic spectra. Unlike molecules, atoms produce line spectra rather than band spectra. So there is a difference that, as we discussed in different spectroscopic techniques, that molecules produce the bands. However, in case of AAS, the atoms produce the line spectra. These lines are extremely sharp and specific, which gives AAS its high selectivity. This is the reason AAS can accurately distinguish between different metal elements. There are several types of atomic absorption spectroscopy depending on the atomization techniques used. The major types include flame atomic absorption spectroscopy, graphite furnace atomic absorption spectroscopy, cold vapor atomic absorption spectroscopy, and hydride generation atomic absorption spectroscopy. Each type has its own advantage and applications. We will discuss flame atomic absorption spectroscopy, graphite furnace atomic absorption spectroscopy, cold vapor atomic absorption spectroscopy, and hydride generation atomic absorption spectroscopy in detail. Now we will discuss the flame atomic absorption spectroscopy. Flame atomic absorption spectroscopy is the most commonly used form of AAS. In this technique, the sample solution is aspirated into a flame where it is atomized. It is suitable for analyzing metals at parts per million levels and is widely used due to its simplicity and speed. While discussing the graphite furnace atomic absorption spectroscopy, uses an electrically heated graphite tube to atomize the sample. It provides much higher sensitivity as compared to flame atomic absorption spectroscopy and is capable of detecting metals at parts per billion level. However, it is more expensive and time-consuming technique. If we see the cold vapor atomic absorption spectroscopy, that is a specialized technique used exclusively for mercury analysis. In this method, mercury ions are chemically reduced to elemental mercury vapor, which is then measured directly without a flame resulting in extremely high sensitivity. Hydride generation atomic absorption spectroscopy is used for elements such as arsenic, selenium, antimony and bismuth. These elements form volatile hydrides which are separated from the matrix and then atomized, significantly improving detection limit. Now we will discuss the main components of atomic absorption spectroscopy. An atomic absorption spectroscopy instrument consists of 5 main components in which a radiation source, an atomizer, a monochromator, a detector and a readout system are present. Each component plays a critical role in the accurate measurements of absorbance. The first is radiation source, then the atomizer which will convert into atoms, and monochromator which we select the single wavelength, detector detects the sample concentration wavelength, and then readout system that will give the spectrum. Then now we will further discuss them in detail. Radiation source used in atomic absorption spectroscopy is typically a hollow cathode lamp. It is element specified and emits radiation corresponding to the absorption emits wavelength of the element being analyzed. So the radiation source is element specific source. In this case, which element is to be analyzed? The hollow cathode lamp will be specific for that specific element, and the that cathode lamp will be also made up of that material, so that the desired wavelength is emitted from the radiation source. So if we analyze the calcium atom, then we will use the radiation source of calcium atom. Now we discuss the hollow cathode lamp. Contains a cathode made of the element of interest. As I already discussed that it will be made of that target element which would be analyzed, which is of element of interest. When a high voltage is applied, the lamp emits sharp spectral lines characteristic of that element, ensuring accurate and selective analysis. So it is operated at low pressure and high voltage is applied, and it produces the characteristic radiation of specific wavelength. Atomization process is the most critical step in atomic absorption spectroscopy. During this process, the sample is converted into free gaseous atoms. Efficient atomization ensures maximum absorption and accurate results. So first the sample is converted into free atoms that occurs in flame or furnace, and it will result in accurate analysis. The nebulizer converts the liquid sample into a fine aerosol, while the spray chamber removes light droplet. This ensures uniform atomization and stable flame condition. Different flames are used in atomic absorption spectroscopy. The commonly used flames in atomic absorption spectroscopy include air acetylene flame, nitrous oxide acetylene flame, and the choice of flame depends on the element being analyzed and its excitation temperature. And now the monochromator isolates the desired analytical wavelength and removes unwanted radiation. This improves selectivity and reduces spectral interference. The detector, usually a photomultiplier tube, converts the transmitted radiation into an electrical signal. So the detector here is photomultiplier tube that converts the wavelength radiation into electrical signal. The intensity of the signal is directly related to the amount of absorbed radiation, and this detector photomultiplier tube has high sensitivity. Now we will discuss the signal processing. The electrical signal from the detector is amplified, processed, and converted into absorbance values. These values are then displayed digitally or recorded by a computer system. Now if we see the interferences, there are several types of interferences which are present and they can affect the atomic absorption spectroscopy measurement. That includes the spectral interference, chemical interference, and ionization interference. These must be properly controlled to obtain the accurate results. Methods to reduce interference. Interferences can be minimized by using releasing agents, protective agents, matrix modifiers, and appropriate background correction techniques. These are methods which are used to reduce the interference. We can use the releasing agents, matrix modifiers. These are the methods, so we can remove the or we can reduce the interferences in the results. Now what is background correction? That is essential in Atomic absorption spectroscopy. It is a common method that includes the deuterium lamp method. The other is Zeeman effect method, which correct for non-specific absorption and scattering. Atomic absorption spectroscopy offers high sensitivity, good accuracy and excellent selectivity. It is relatively simple to operate and require less sample preparation compared to many other techniques. So it is a very high sensitivity technique and it gives accurate results. It is element specific, as already discussed, that which element is analyzed, the radiation source will be of that element, and it will be very useful for giving the accurate and results, and highly sensitive technique, so it can analyze the minute concentrations, trace elements, and it is simple and rapid technique, that is very good analytical technique and accurate, accurate results. Now we will discuss the limitations of atomic absorption spectroscopy. Atomic absorption spectroscopy has also limitations such as a single element analysis, as only the cathode lamp is mostly used, which is made up of single element, so single element analysis is carried at one time. Limited non-metal analysis and the requirement for sample digestion. For the atomic absorption spectroscopy, the sample is digested and then the sample is analyzed by atomic absorption spectroscopy. Now applications of double AS are widely used. They are widely used in environmental monitoring, clinical chemistry, food analysis, pharmaceutical analysis, metallurgy and industrial quality control. In the case of environmental analysis, atomic absorption spectroscopy is used to detect heavy metals like heavy metals present in water like lead, cadmium, mercury and arsenic in water, and soil and air samples. So it is useful for the soil contamination studies and pollution monitoring also. If we compare the atomic absorption spectroscopy to UV visible spectroscopy, then atomic absorption spectroscopy is more selective than UV visible spectroscopy. However, techniques like ICP, OES and ICP-MS allow multi-element analysis but are more expensive. So it is a cost-effective technique. It gives accurate result, but it is very selective, and one element is detected at one time, which becomes its limitation. Atomic absorption spectroscopy is highly reliable and widely used analytical technique for metal analysis. Its simplicity, sensitivity and accuracy makes it an essential tool in modern analytical chemistry. Thank you for your attention.